Okay, so in the last lecture, we talked about unconstrained convex optimization problem. Right? That is sort of the simplest problem you can think about. Since it's unconstrained, you can use the automatic conditions, and we talk about two types of method. The first order method only use the gradient information, and then the second order method use the Hessian information, right? And all those methods can be derived using Taylor series expansion and so forth. Okay, so just sort of like a structure of this course, we will start from unconstrained optimization and gradually add complexity to the optimization problem we consider, right? At the end of the day, we will talk about mixed integer nonlinear program, which is sort of the most general optimization problem we will cover in this course, right? So the one natural question to ask is, after talking about unconstrained optimization, what is the next level of complexity? Right? So we will spend around 4 lectures talking about a type of problem called linear programming. So if you want to know a little bit more details about linear programming, there is a course in industrial engineering you can take. It will spend the whole semester just focus on linear programming. Okay. So what is linear programming? Typically, you can think about linear programming as minimizing or maximizing a linear objective function subject to some linear constraints. Okay, so here's a linear programming where you have 4 variables, x1, x2, x3, and x4. The objective is a linear function of the x1, x2, and x3. And then you can have linear constraints, right? So you can have less than equal to constraint, equal to constraints, or greater than equal to constraints, or some non-negative constraints on some of the variables. Yeah, so this is sort of an illustrative example of what a linear programming problem is. Now, how do you represent that in a general way? So this is a representation of linear programming. We will talk about different ways of representing linear programming. This is perhaps one of the most natural way, where you have x, which is, let's say, n-dimensional real variables. The objective is minimizing C transpose x. Then you have different sets of constraints, right? We are denoting the set of constraints by M1, M2, and M3, where M1 is the set of greater than equal to constraints. M2 is a set of less than equal to constraints. M3 is a set of equality constraints. Okay, and then you also have some non-negative constraints on the variables, and then some of the variables may be less than equal to 0. Okay, so that's sort of the most general problem you could consider. Now, there is as I said, there are different ways of representing a general linear program. This is a reformulated problem. We will show you real quick. This is actually equivalent to the previous formulation, right? So here we have C transpose X subject to a matrix A, which is a M by N matrix, and B is a right-hand set vector with dimension M, right? So you can represent any linear program in this general form, which is AX greater than equal to B, right? So you may be wondering, they are equality constraints, they are also less than equal to constraints, right? How do you represent things in this general form? Well, it is quite straightforward to transform the general formulation we talked about in the previous slide into this formulation here. Okay, so here let's talk about the first set of constraints in M1. They are already greater than equal to constraints, so you don't really need to make any changes, right? And for the constraints in the second set, initially they were, less than equal to constraints, right? But then you can always multiply by -1 on both sides of the inequality, then they will become greater than equal to, right? And similarly, if you have equality constraints like this, you can write an equality as greater than equal to and less than equal to. And for these less than equal to constraint, then you multiply by -1, right? So you sort of convert this equality constraint into two greater than or equal to constraints. Okay. And xj greater than or equal to 0 is already in ax greater than or equal to b form. Then xj less than or equal to 0, you can multiply by -1. That will convert everything into this sort of greater than or equal to form. Right? Should be pretty straightforward. Okay. Any questions regarding this very simple reformulation? Okay. And similarly, as you can imagine, you can also write any linear program as minimize C transpose X subject to AX less than or equal to B. Right? It's equivalent to the other formulation. It's just A matrix will be the negative of the A matrix on the left-hand side. Okay. So let's just give you some heads up on the properties of this linear program. We'll talk a little bit more detail. When is this linear program unbounded, meaning that the objective can go to -infinity? When is this linear program infeasible, meaning that no feasible solution exists? Right. So just a very quick check using some basic knowledge of linear algebra. Right. When is this? Just pick a special case where this linear program is unbounded, right? So I argue that in most applications you deal with, right, the optimization problems are usually bounded, right? If you want to solve a problem where the objective is -infinity, it is sort of a little bit trivial. You don't solve a practical problem where there are no solution exists, or solve a problem where the objective goes to infinity. Right? It's not that interesting. So for those, for most applications, the optimization problem is feasible and bounded. Right? So I would argue that in most applications, A has a full column rank. Right? So when A does not have full column rank, what would happen, right? It can be the case that you have fewer rows than the number of columns, right? So you have fewer number of constraints than the number of variables, right? In this case, A does not have full rank. And then in this case, you can quickly show that there exists a vector V such that A times V equals to 0, right? Because the columns of A are linearly dependent, right? If A does not have full column rank. So if it happens to be the case that C transpose V does not equal to 0, then this problem can sometimes be unbounded, right? Because you can take V to infinity, right? Using the same direction, since A times V equals to 0, as long as you find a feasible solution, then you can move in the direction of V and let the objective go to infinity. Okay, so that's sort of the intuition here. I want to give you a simple example. If you don't fully absorb that, it won't be any problem, and we will talk about revisit those concepts again in the next few lectures. Okay, so the takeaway is that typically in a linear program, you have more inequality constraints than the number of variables. Right? Otherwise, it is very likely the problem is unbounded. Okay, so as you can imagine, there are different reformulations of linear programs. One of them is the following form, where you could separate the equalities and the inequalities. Right? That's another form you'll probably see in the literature, where G is a matrix, H is a vector. Okay. So in particular, I want to talk about what given form of linear program, it will be used to develop what is called a simplex algorithm to solve the linear program, which is called the standard form of the linear program. It looks like the following. Right? So it says we have a linear objective, and then there are a bunch of equality constraints. And all the inequality constraints are x greater than or equal to 0. Okay. So this is what is called the standard form of a linear program. Yeah, you can show that any linear programs you want to formulate can be translated into the standard form. Okay, so this might be a little bit counterintuitive because you can have any arbitrary linear inequality constraints, right? But now you are restricting the types of linear inequality to x greater than or equal to 0, right? There are no other linear inequality constraints, right? So I will show you in the next few slides why any given linear programs is equivalent to this form, okay? Another note here is that usually we assume the rows of A are linearly independent, right? Typically, we have the number of equality less than the number of variables, right? So imagine if you have the same number of equations as a number of variables, you are solving a linear system. There is no degrees of freedom. If A is full rank, then you just do multiply in inverse, then you get x. Right? So this is also a trivial problem. So typically, the number of equations you have is strictly less than the number of variables. Right? You can imagine each single equation will remove 1 degrees of freedom. Right? So if you have n equations that will remove n degrees of freedom, meaning that you only got one single solution. Right? And then if you have conflicting equations, right? This problem can be infeasible. As I said, usually we are not that interested in dealing with infeasible problems or unbounded problems, right? So therefore, typically you can assume if you have a linear programming model, in practice you have m strictly less than n. Okay. So now we will talk about how do you convert any linear program into the standard form. Okay, so this is a recipe of converting any linear program to the standard form. Right? First of all, as you can see, all the variables involved in the standard form are greater than or equal to 0. Right? In other words, there are no free variables. There are no variables whose domain is in Rn. All the variables are greater than or equal to 0. Right? So the first thing you want to do is you need to convert the variables whose domain is in Rn into the greater than or equal to variables. Right? So here, so one simple thing to do is if a variable xj in the problem is unconstrained, then you can replace it by xj plus minus xj minus, right? So any real variable can be represented as a difference of two non-negative variables, right? Okay. And then now you can impose the constraint on xj plus and xj minus, right? So that the underlying idea is any real number can be written as the difference of two non-negative numbers. Okay. Now, the other thing you want to think about is to eliminate the inequality constraints, right? So if a constraint is written in A transpose X less than or equal to B or A transpose X greater than or equal to B, you want to convert them to equality constraints, right? So because remember in the standard form, the only inequality constraints are X greater than or equal to 0. Right? There are no other types of more complicated inequality constraints. So if you have a more complicated inequality constraints, let's say you have the summation of aij xj, j from 1 to n, less than or equal to bi, right? Where it's not a simple bound constraint. Then what you can do is to introduce a new variable sj, where sj is si is greater than or equal to 0. Since the left-hand side is less than or equal to bi, but if you add any arbitrary greater than or equal to variable, you can change this to an equality constraint, right? The reason is si is kind of like a variable that describes how much slack you have on this inequality, right? So if the difference between bi and the left-hand side, we know that it is strictly greater than or equal to 0, but how much is it greater than or equal to 0? You can have a variable si to describe the difference. But what we do know is that si has to be greater than or equal to 0. Right? So now with this trick, as you can see, we introduce a new variable to eliminate this less than or equal to constraint. Now we end up with a constraint in this equality form and a variable that is greater than or equal to 0. Right? So this is consistent with the standard form. And similarly, if you have a greater than or equal to constraint, you can add similarly you can add a slack variable, but you have to minus si instead of plus si on the left hand side. Right? Similarly, you set si greater than or equal to 0. Okay. So with that, you will convert any linear programs into standard form, right? Because now, as you can see, following these two steps, the inequalities are converted to, and any linear program can be represented using inequalities. Then the inequalities are converted to the standard form. All the variables are greater than or equal to 0. Right? You eliminate the free variables. Okay. So with that, we will talk a few applications of linear programs. Yes?
So since we're adding like this new variable s, is that like whenever we're going to do an actual optimization problem, like through Gurobi or whatever, does that mean we're going to have to add like a new set of variables to our problem?
Right.
Sort of introducing this slack thing?
Yeah, that's a very good point. You don't need to do that. Groovy automatically does that for you. Right? So you don't. So you can formulate your linear programs in any arbitrary way as long as it makes physical sense or logic sense. But then the reason we introduce the standard form is because the most commonly used algorithm to solve linear programs relies on the standard form. So underneath the hood, Groovy will automatically convert any linear program you formulated into the standard form. Then it will call this standard algorithm to solve the problem. Right? So we will talk about this algorithm in maybe 2 or 3 lectures from now. Okay. Yeah, that's a good point. Yes.
Does it matter that the solution for when we introduce xj plus and xj minus, so it's not unique? We have like linear arbitrary combination. Is it important, and what the solution will be? Will it be just to any random numbers?
Yeah. So if you so the solution typically depends on the algorithm. Right? We can talk a little bit about that after we introduce the algorithm. Typically, if you use simplex algorithm, the solution is obtained what is called at an extreme point of this polytope. Okay, so the solution is sort of unique if you if you use simplex algorithm and the problem is not degenerate. But if you use log barrier method or other type of method and the problem is degenerate, you could get a non-unique solution. Right? But then I wouldn't say the introduction of the slack variable will change the solution, because after you project it back to the original space, you still get a unique solution if the solution in the original space is unique.
Not slack variable, but when we instead of like an unconstrained, we have xj plus and xj minus to introduce. So it's not like introduce slack variable, right?
Oh yeah, you are not.
Instead of one,
right.
we have two.
Yeah, sorry, I shouldn't call that slack variable.
Yeah.
So you introduce 2 variables, but then like you said, the solution in the this xj plus x minus space may not be unique, but if you use a particular algorithm, it might be unique. Okay. Any other questions here? Okay, so in the next, let's say, 15 minutes or so, we will talk about some applications of linear programs. Right? So usually when I introduce a new topic, we will start with some engineering applications because they are sort of intuitive. And then we will talk about the mathematical properties of this type of problem. Right? right? So the last thing we talk about is the algorithm to solve this type of problem. We will sort of follow this routine throughout this semester. So here we will talk about 5 different problems, including problems in chemical engineering, electrical engineering, in control, and also finally, there is a very interesting application of linear programs to represent one and infinity norms. So we will show you how to formulate one norm and infinity norm using linear programs. Yeah, so this lecture should be pretty straightforward. There are not much math involved. I just want to give you some intuition of how to formulate linear programming problems. So the first problem is called a production problem. You can read a little bit about this context. Basically, a firm produces n different goods using m different raw materials. Okay, let Bi be the availability of the amount of ith raw material. The jth good, j from 1 to n, requires aij units of the ith raw material and results in a revenue of Cj per unit produced. Right? So the firm faces the problem of deciding how much of each good to produce in order to maximize its total revenue. Right? So the high-level idea is a company, any company would want to maximize its profit, right? But then you have limited resources. Maybe you have different types of resources like time or space and so forth, right? And then each type of goods will consume a Aij amount of resources, right? You are going to run the company at limited resources while maximizing the profit of this company, right? So this is sort of a very simple problem. You will sort of face this type of problem in your life as well, right? You are always constrained in time or resources, but then you try to maximize a given objective, right? Of course, your objective is not as simple as maximizing profit. You have different profit to different types of objective you want to maximize, but then how do you rationally allocate your resources such that you can maximize your objective? Okay, so this is a simple problem. I will give you the formulation right away. The objective is to maximize the summation of profit this company can make by selling different types of products. Right? So it's a summation of Cj, Xj, right? And on the other hand, you have some sort of resource constraints. Okay? We are, for each type of resource, Bi, the total consumption of resources by selling these products or making this product has to be constrained by the availability of each resource you have. Right? And of course, Xj has to be greater than or equal to 0 because you cannot produce negative amount of product. Okay. Yeah. So if you remember, this problem is very similar to the knapsack problem we talked about before. Right? So the only difference is that in knapsack problem, xj's are binary variable. Right? Whether you put this item into your knapsack or not, right? And your knapsack has a capacity. So here is like a continuous version of the knapsack problem. Right? That's why you can formulate it as a linear program. But if you force xj to be binary, this is exactly the same thing as the knapsack problem. Okay. Yeah. So here, I'm going to give you a very concrete example of the production planning problem using this farmer's example. I mean, it is almost identical to this general formulation, but the main reason I want to give you this problem is I want to give you some numbers such that you can observe a very important geometric property of linear programs. Okay, so I will show you some geometric intuition later on using this example with real numbers. Okay, so now let's suppose a farmer has a piece of farmland, say L square kilometers, to be planted with either wheat or barley or some combination of the two. Right? So these sort of are like the two products the farmer can make, right? And then you are constrained by the size of the land. The farmer has the limited amount of fertilizer as well, F kilogram, and pesticide, right? So you have 3 different resources: land, fertilizer, and pesticide, right? And then you have 2 products to make, which is wheat and barley. At the end of the day, you want to maximize the profit by making these 2 types of products. Okay. So here's a 2D problem, right? You have 2 variables, x1 and x2 represent the area of land planted with wheat and barley, right? 2 continuous variables, x1 and x2, greater than or equal to 0, you maximize the profit. And here's the sort of the 3 capacity constraints, or knapsack constraint on area, fertilizer, pesticide. These variables have to be non-negative, right? Okay, so hopefully this should be very obvious. So let's plot the feasible region of this problem and the optimal solution of this problem by making up some numbers, right? And then you will get a key observation from this problem. All right, so here the x-axis is x1, the y-axis is x2, right? Now we know that the feasible region must be in the first orthant, right? Because x1 and x2 are non-negative. So what about the 3 resource constraints, right? So here in this case, we are denoting the 3 constraints in 3 different colors, right? Red, blue, and green. So here's this red constraint, and this is the green constraint. This is this blue or purple constraint, right? So as you can see, the feasible region of this problem is essentially this particular region denoted by, in total, we have 5 constraints, right? So let's say you don't know any optimization algorithm to solve a linear programs. What if you want to solve it by hand? Maybe you have studied this when you were maybe in high school, right? You can push a ruler all the way up and see which point you can hit at the end. Right? I remember I studied this in high school. Okay, so how do you decide which point is the optimal solution? Here, I'm showing some contour curve of the objective function, right? So as this contour curve goes to this particular direction, the objective is going to increase, right? So the points on this curve will give you the same objective solution, right? So similarly, if you lie on this dashed line here, that gives you the same objective solution. So what you can do is you push this curve to this direction that is perpendicular to the dashed line, right? And see how far you can get until no point will lie on this dashed line, right? That's what you would do if you haven't studied anything about linear program, right? So one thing you would note that the optimal solution, which corresponds to this particular curve here, this particular dashed line here, will only hit 1 point in the feasible region, which is this point here, right? So what happens here is the optimal solution of this linear program lies on the vertex of the feasible region. Actually, you can show, we will show you in the next lecture, there exists a vertex that is optimal for the linear program, right? So if a linear program is feasible and bounded, you can show that there always exists a vertex that is optimal, right? In fact, in this example, that vertex is unique. Okay. So when is a solution non-unique in this particular problem? So I would argue that this solution is not unique if this particular boundary is parallel to the dashed line, right? So then you will have not just an optimal vertex, but an edge of this polyhedral that will always give you the optimal solution. So this is something called degeneracy in linear program, where you have more than one solution that is optimal, okay? But if the problem is not degenerate, right? So if your constraint, none of your constraint is parallel to the objective, then you can show that you always have you always will have a unique optimal solution, okay? That's some sort of geometric intuition. Now let me show you another example in the electrical engineering sector. Actually, in chemical engineering, there are similar applications. So this is called multi-period capacity planning problem, right? So what at high level, what that means is you need to expand the capacity of some sort of facilities, right? For example, in electrical engineering, you may think about building more power plant, right? You may read the news that there are blackouts in different states, especially in California and Texas, right? So that means you have a shortage of power sometimes. As population grows, or if you read the news, there will be more data centers being built in the future, right? The electricity demand is going to increase. So therefore, you need to find a way to expand the capacity of the power generation such that you can satisfy the growing demand, right? This is a case in many areas, like let's say if you are sort of an e-commerce company like Amazon, you want to build more warehouses to satisfy the growing demand, right? So where and when you are going to build those warehouses, right? So let's use this electric power sector example to explain the idea of this model. Right, so let's suppose a state wants to plan its electricity for the next T years. The state has a forecast of DT megawatts for year T, right? That's a demand of electricity at year T. And the existing capacity, which is in oil-fired plants, will not be retired and will be available during year T is ET, right? So that sort of, that now we are converting fossil fuel-based plant to renewables. So perhaps you are not going to build more oil-fired plants. So you can assume the remaining capacity of this oil-fired power plant at year T is E sub T. And now let's assume there are two alternatives for expanding the electric capacity because the oil-fired are not going to be expanded, right? So for the sake of the argument, we assume these two alternatives are coal-fired and nuclear power plants. Of course, you are not going to build coal-fired power plants nowadays, probably things like solar and wind, right? So just for the sake of this problem, we assume you are going to build more coal and nuclear. And we have the capital cost, CT per megawatt of coal-fired capacity that becomes operational at the beginning of year T. And then the capital cost for nuclear power plant is N sub T. And then for various political and safety reasons, it has been decided that no more than 20% of the total capacity should ever be nuclear. Okay, and coal plants last for 20 years, while nuclear plants last for 15 years. Least cost capacity expansion plan is desired. So this should be a very simple problem to consider, right? You want to expand the capacity of two types of plants while satisfy the growing demand. So here's some notations where you have the forecasted demand, the existing capacity, the capital cost of the two types of plants. Then the decision variables include the new capacity you are going to build for coal and nuclear at year T, right? And you can introduce some additional variable to denote the total capacity available in year T and the total nuclear capacity available in year T. Okay, since you have this sort of political constraints saying that nuclear capacity cannot be greater than 20%. Yeah, so here's the formulation. You have the objective as minimizing the total cost, and there are conditions for coal and nuclear plants capacity, right? So since coal plant lasts 20 years and the nuclear plant lasts 15 years, right? So you are taking them. When you take the summation, you are take the max of from 1 to T minus 19, right? Because if after 20 years it will not exist anymore. And similarly for nuclear. And you have the sum of the capacity must meet the demand. Then the other constraint is the limitation for nuclear capacity, where the ratio of nuclear divided by the total capacity is less than equal to 0.5. Of course, you can convert this into a linear inequality. So if you can convert a problem to linear inequality, never model it as a fraction inequality, right? Okay, so this is still a linear program. Okay, so hopefully the previous example is clear. So now I'm going to talk about an example probably it is very familiar for chemical engineers. If you're not a chemical engineer, I will explain it real quick. So this is called a continuous stirred tank reactor model. So the reason I want to introduce this problem is I want to sort of give you a little bit connection of linear programs with what is called model predictive control. Right? So control is a major area in process systems engineering. Nowadays, of course, if you work on things like robotics, control is a major topic, right? So the intersection of control with optimization is usually named model predictive control. Basically, you solve an optimization model to decide which control actions you are going to take, right? So let's say when you try to decide how the robot will move its arms, right? So you solve an optimization problem to decide what input you are going to give or what signal you are going to give to the robot such that the robot will move the way you want it to move, right? So in chemical engineering, we are, of course, dealing with controlling chemical plant. Okay. So in the next 15 minutes or so, I will give you a quick overview of what is model predictive control and roughly how it is applied in chemical engineering. Right? So if you work on, let's say, electrical engineering or civil engineering, there are similar problems. The underlying philosophy would be the same. It's not possible to give you everything related to model predictive control. You can teach a whole semester class just on model predictive control itself, right? Unfortunately, we don't offer it in this department. Okay. So usually when you have a control problem, there is an underlying simulation problem as well, right? Because you want to implement your controller. Before you test your controller to a real chemical plant, you want to simulate your controller in what is nowadays there is a buzzword called digital twin, right? So there might be some equations that can represent this chemical plant, right? So before you implement your controller, you want to sort of see how the controller work in a simulation model. Okay, so the CSTR is perhaps the simplest chemical process you can think about. So the idea is the following. You have a reactor which will produce some chemical product. Right? So the input to the reactor are some flows of chemicals. Right? So the flow rate are denoted by F0, the temperature is denoted by T0, and C0 denotes the concentration of the raw material to this reactor. Right? So at this reactor, you assume a perfect mixing. Right? The concentration of you may have concentration of chemical A, B, or C. Right? Let's assume the concentration is uniform in this reactor because you have something that is stirring in this reactor. Then after the reaction, you will have some product exiting the reactor, you denote the product as flow rate F, temperature T, concentration C, right? So what goes in, some products will go out, right? As you know, some of the chemical reactions may emit heat, right? If you do not use any cooling water, this reactor may explode. So therefore, you put some cooling water to cool down the reactor. So the cooling water temperature is denoted by Tc, right? And H denotes the height of this reactor. You want to control the reactor such that the height remains almost constant despite some noise, okay? So before we talk about how to control this reactor, let's talk about the physics underlying this reactor, right? So you can represent the physics of a chemical reactor using ODEs, right? Actually, if you make fewer assumptions, you might need a partial differential equation. But here we make a simplifying assumption saying that the concentration is uniform, right? So then you can reduce that to ODEs. I'm not going to the physics. If you are chemical engineers, those things should be very easy for you, right? So if you want to consider how much the concentration of in the CSTR will change, it's basically you have some in and out, flowing in and out, as well as some sort of reaction. Right? So, if you're not a chemical engineer, don't worry. Those are just imagine this is an ODE system. Okay, and similarly, you have ODEs related to the temperature. There are things related to the in and out of the flow. This is sort of the heat of the reaction, right? And then this term is related to the cooling water. Okay, and then the height of the reactor is only related to the in and out of the flow. Okay, so those are the ODEs. So as you can see, ideally, one would like to optimize this ODE system to decide what you are going to input to the reactor. Right? So the goal here is to take the state of the system to a constant set point or time varying set point trajectory by optimizing the input. Right. So again, usually you want this reactor to operate at steady state. You don't want flows to change too much. You don't want the height of the reactor or the temperature to change too much. Okay, so how do you maintain the reactor at steady state? Yeah, you could change the coolant flow rate, right? That's something you can change. You can make the coolant flow rate higher, then the temperature of the reactor will reduce, right? And then the output flow can also be changed, right? So these are the two things you can manipulate. But you want the things you can measure to operate at steady state. For example, you can maybe measure those concentration, or you can measure temperature and so forth, right? So if you want those variables to operate at steady state, ideally you want to optimize the ODE directly because they are a very accurate description of what's going on in this physics-based system, right? But optimizing over ODEs is very challenging. Right? We are not even covering how to solve optimization problem with ODE constraints in this course. Right? You can imagine it's a quite challenging problem. So therefore, in practice, you can use a linear model to approximate the dynamics of the ODE. Right? So remember, linear programming model have finite number of variables. Right? If you have an ODE constraint, you sort of have infinite number of variables over the trajectory of the time. Right? So how do you approximate the ODE system using a linear programming model? We are not going to cover that in this class. This is called system identification problem in control. You can assume someone did some experiment and come up with a linear programming model that approximates this ODE system very well. Right? Since the ODE system is also nonlinear, it is not trivial to have some linear equations that approximate the ODE system. Right? So if you are familiar with Since like machine learning, you can think about you generate a bunch of data from the system, and then you use a linear model to fit the data. Right? That's one of the ways you could approximate the dynamic system. Okay. So what is model predictive control? Typically, people refer to these type of problems where you have a system that that is dependent on time, t from 0 all the way to t minus 1, where xt denotes the state of the system at time t. Right? The initial state should be provided from the measurement. Right? So let's say if t equals to 0, which means the measurement at the current time, you can measure those states using some sensors. And yt is some system output, right? Oh, yeah, sorry. So x are the state, yt are the states that can be measured, right? So if all the states can be measured, then you have basically the same matrix equals to the identity matrix, and then yt equals to xt. So typically you can assume it is true, but let's assume your system is not fully measured. Your yt might be a subset of xt. Okay. And ut are the input variables that can be manipulated to determine the future state. In this case, the UTR, the TC, and the flow, right? So those are the variables that can be manipulated. So typically, when you solve a model predictive control problem, people assume at steady state, all these variables equals to 0, right? So if at steady state, the absolute value are not equals to 0, you can always normalize them and then assume at steady state, all these variables equal to 0. And then the objective penalize the deviation of the output from the steady state. Okay, and then also penalize a change in the control actions. You don't want to change your control variables too frequently. And both the states and the input may be subject to some linear constraints of this particular form. Okay. Yeah. Any questions? Yes.
I'm sorry, I might just not have heard correctly, but so our y is what we're trying to control and our u is our manipulating?
Yeah, so you can think about it that way. So the u is what you can manipulate, like the coolant temperature or the flow rate, right? Y is what you can observe, right? So actually, yeah, x is what you are trying to control at a steady state. So x describes all the state variables. If all the x can be measured, then y equals to x. Right? Maybe, for example, you want to control both the height of the reactor and the temperature of the reactor. Right? So let's assume you can only measure the height. You are too poor to buy a thermometer to measure the temperature. Right? So in this case, y is one dimension lower than x.
So okay, so they're allowed to be different dimensions.
Yeah, they are allowed to be different dimensions. Let's say you have a sensor on each of the state variables, then y equals to x. Okay.
And then my second question would be like, I guess I'm familiar with the use of like the dot inside the parentheses.
Yeah.
Does that just denote that it's like at the current time?
Yeah. So let's assume t equals to 0 is the current time. Right? You did some measurement at t equals to 0, but then the model predict control is telling you what you should do in the future.
Yes.
Right. So how are you going to change your coolant flow rate in the future? Let's say, right. So now you at t equals to 0, you solve an optimization problem like this to say from now to 10 minutes from now, what is the optimal control action I should give to my reactor such that my reactor can operate at steady state?
Yes.
Okay.
So I guess what is the dot referring to then?
The dot? Oh yeah. So the dot, you can imagine this as t from 0 to a capital T.
Okay.
Right. So you,
capital T.
yeah.
Gotcha.
So yeah.
That makes sense.
Yeah. So this means t equals to 0 to capital T. That means you are optimizing all those variables simultaneously in this problem. Okay, yeah. Thanks for asking. Yeah. Any other questions? Okay, again, it is not possible to tell you everything related to it. It is a separate subject. You could take a few courses on this subject. In our department, Professor Zoltan Nagy is an expert in this type of research. Okay. Yeah. So now there is another application in linear programs I would like to talk about briefly, called multi-commodity flow problem. Right. So this problem is quite commonly used in transportation and in telecommunications. So let's assume you have a network represented as a directed graph. Right? Does everyone know what a graph is? Right? So a graph means you have some nodes. Right? So those are nodes in a graph. So the nodes is denoted as this set V, right? You can also think about V as vertices, right? So those are the vertices in this graph. And E denotes the set of edges, right? So in this case, we are talking about directed edges. An edge can connect any two nodes in this graph. And in this case, an edge has a direction, right? So like say here, this edge has a direction. That means if you have some sort of a product at this location, it can only flow to the X node in a given direction. It cannot flow back. Okay, yeah. So that's why those edges are directed. And you have multiple commodities need to be transported across this network. Here we have a set of nodes. We call it X1, S2, and S3. Those are called source node. For example, you have some product you want to ship to your destination, right? Let's say here you have 9, 2, and 3 different quantities of products, and then you want those products to flow using this network such that you deliver those products to these 3 different destinations. Okay, it's like a network flow type of problem. But then the thing is that each edge has a capacity and a cost, right? You can think about each edge as a transportation link, right? If you're dealing with transportation problem, you want to ship some product from some warehouses to, let's say, customer destinations, right? Maybe there are some intermediate warehouses you have to deliver to. But then the capacity are constrained by the number of tracks you have between source S1 and this node X, right? That's what this physical means. And the cost per unit of the commodity associated with each edge is denoted by C sub E, right? For example, if you ship some product from A to B, then the cost would be dependent on the distance between A to B, right? Or the ways of transportation you use. And each commodity K has a demand dk from source Sk to a sink Tk. Okay. Yeah. So how to formulate this problem? The major decisions you are going to take is how much commodity is being shipped through each edge, right? So that's why we use this E to denote, subscript E denotes the edge, K denotes a given type of commodity. Okay. And then what constraints do you have? First of all, you have those capacity constraints, right? If you sum over all the K, K are the different types of commodities, sum over all the commodities at a given edge, it should be less than or equal to the capacity of the edge, right? Then the next constraint you have is called flow conservation constraint, right? So you have some demand at the customer node. You need to satisfy those demand. And then you also have some, let's say, product at the source node. You must ship them out. But then as for those intermediate nodes, it does not have demand. So that means what goes in has to go out, right? So there are 3 different types of node. Here, if, let's say, if the node V is a source node, then what goes out minus what goes in should be equal to what you have at this particular node you want to ship out. Right? So on the other hand, if the node is at a sink node, that is a customer node, then what goes out, this should be, what goes out minus what goes in should be a negative number, right? And on the other hand, if it's an intermediate node, what goes in minus what goes out should be equal to 0, right? So this is essentially what this constraint is about. You can read a little bit detail into the index of those variables. And at the end, you want to minimize the total transportation cost, right? So that should be a quite simple problem. So finally, I want to talk about this application on norms, representing norms in using linear programs. This is actually the most important application I want to talk about in this lecture, because it gives you some insight on what linear programs can represent, and also it can help you understand convexity better, right? So again, as we studied in the second lecture, we talk about those norm functions or norm sets, right? And then, we know that this function, x norm, is a convex function, right? And then this is a way to define p norm, right? Of course, you cannot represent any arbitrary p norm using a linear program, like 2 norm, right? It is very clear 2 norm needs some sort of quadratic constraint, right? It's not linear. But then you can show that for some of the problems that involve infinity norm and 1 norm, they are linear program representable. Okay, so just to refresh your memory, the definition of infinity norm is taking the maximum of the absolute value of each component of vector x, okay? And then 1 norm is the summation over the absolute value of each entry of vector x, right? So as you can see, this is a sort of a piecewise linear function, right? Because you have some absolute value. How do you plot absolute value? So the absolute value function looks something like this, right? This is 0, this is x, right? It is not a linear function, it is a piecewise linear function. So then we will talk about when this linear function is a linear program representable, right? But as you can see very clearly, it is a convex function, right? So let's first talk about how do you reformulate minimizing the 1 norm into a linear program, right? So let's suppose you have the following problem. You are minimizing the 1 norm of x subject to some linear constraints, okay? Right? So this is clearly not a linear function, right? The objective has to be C transpose x for it to be a linear function. So this format itself is not a linear program. It is a sort of like, let's call it piecewise linear program, but no one named linear program that way, right? So this is a piecewise linear function, not a linear function. So how do you reformulate this into a linear program? So what you can do is introduce a new variable z, where z is in Rn as well, okay? Such that you force each element of zi to be greater than or equal to the absolute value of xi, okay? So how do you force zi to be greater than or equal to the absolute value of xi? Right?
The sum of all the numbers.
Yeah.
If my zi is greater.
Right. So if you want, say, zi is greater than or equal to the absolute value of some number, you just need to let zi greater than or equal to xi and zi greater than or equal to minus xi, right? Right. So that this can be converted to two linear inequalities, right? So you let zi greater than equal to xi and zi greater than equal to minus xi. And now you're replacing objective with the summation of zi, right? So why this is a valid formulation, right? Since with these inequalities, you can only enforce zi to be greater than equal to the absolute value, right? You cannot force them to be exactly equal to the absolute value, right? So the trick is you are minimizing, right? Because you are minimizing zi, right? And zi is greater than equal to the absolute value of xi. Then at the optimum of this problem, zi will always equal to the absolute value, right? There are no other constraints you enforce, okay? Okay, so this is a trick we will use. But now, let's think about the following problem, right? If I give you this problem, right? So this is a separate problem. Think about if we are maximizing the one norm of x subject to ax less than or equal to b. Can this problem be reformulated as a linear program? Yeah, so what's a tricky thing here? Any thoughts? Someone said no. Why is that?
Well, we can minimize minus norm, so we can just put minus signs in
Mhm. Yeah,
the objective function.
okay.
And
So here, yeah. So here's the trick here. You can only reformulate as a linear program if this coefficient is positive. You are minimizing a positive coefficient of the norm, right? So let's say if you are maximizing, okay? What happens is that if you use this reformulation, you can only enforce the zi you introduce is greater than or equal to the norm, the absolute value, right? So and now if you are maximizing, zi will go to infinity, right? That's the only constraint. The constraint you enforce is, zi is greater than or equal to absolute value rather than zi strictly equal to the absolute value with these two constraints you have here, right? So but if you are maximizing, then it is not bounded above, right? The zi is only bounded below, right? If you are maximizing, it will go to infinity. It will not be exactly equal to the absolute value. Okay. Yeah, that's a trick here. Any questions?
So wait, so in conclusion, you can't do that? Like,
You cannot do that.
okay,
Right, so
is
it
that
will.
like, would you call that like an unbounded problem? Is that one that?
Yeah, so you cannot formulate it using linear programs. It may not be an unbounded problem. It just if you use this particular way to reformulate this problem, it will be not equivalent to the original problem.
Got it.
Okay,
So
yeah.
you would still like get a solution, it's just not right.
Yeah, but then so you have used some other ways like mixed integer programming to reformulate that, right?
Gotcha.
Okay. So there is another quick way to think about why maximizing this function cannot be formulated as linear program, right? So remember, linear program is a special case of convex optimization problem, right? Objective is linear, constraints are linear, right? So here, if you have this minimization over one norm, the objective is a convex, right? One norm is a convex function. If you are minimizing a convex function, that is a convex optimization problem, right? On the other hand, if you are maximizing a convex function, it is not a convex optimization problem. Right? Since linear programs is a subset of convex optimization problem, then you know that in theory, there is no way this can be formulated as a linear program. Okay, so again, minimizing convex function subject to convex constraint is called a convex optimization problem, right? So if I'm maximizing a convex function subject to convex constraint, it is not a convex optimization problem, right? So think about you're maximizing a quadratic function which is convex, it could be unbounded, right? If you're minimizing a quadratic function, right? A quadratic function whose Hessian is PSD, then it is a convex problem. Okay.
I guess so then
Yeah.
if we're like maximizing like a concave function.
Yeah, exactly.
So that would be
Right.
sort of like kind of flips once
Mhm.
you get
Yeah, exactly. So if I'm maximizing minus x1 norm,
then that's
then that's fine here.
Okay,
Yeah.
gotcha.
Okay. So with a similar trick, you can also reformulate minimizing the infinity norm of x into a linear program. Again, infinity norm represents the maximum over the absolute value, right? So if you set a single scalar t to be greater than or equal to the absolute value of xi for all I, then you can use this to represent the infinity norm, right? Again, the trick here is since you are minimizing, but you have t greater than or equal to each absolute value, right? Because you are minimizing, t will always take the minimum it can take, right? So that's why it is linear programming representable. Okay. So what about if you have absolute values in the constraints? Can you represent that using linear programs, right? So sometimes you may want to model absolute value in your optimization model. Like how do you, when it can be reformulated as linear program, when it cannot, right? So let's just suppose you have this generic form where you have ai times the absolute value of xi less than or equal to bi, right? So let's write this as a less than or equal to constraint. What I can argue is if all the coefficients ai are greater than or equal to 0, then you can reformulate this absolute value problem using linear program. If one of the ai is negative, then that is not the case. Okay? So that actually follows the same rationale as the minimization problem, right? Because you have absolute value on the left-hand side, right? So you have a less than or equal to constraints. Then in order to satisfy this less than or equal to constraint, the optimizer can always push this zi variable to be as small as possible, right? It's the same rationale as minimizing the one norm, okay? Yeah. So another takeaway you will find out in the future is that when you have a convex function on the left-hand side of a constraint, right? If you write a constraint fx less than or equal to 0, when f is convex, then the feasible region is convex, right? We talk a little bit about that, this property in the convex set lecture, right? So this is like saying, if a function is convex, we know that the epigraph of that function is convex, right? So this set is nothing but taking the intersection of the epigraph with t equal to 0. Right? So that's the intersection of two convex sets, or some people call it a sub-level sets of convex function. You can refer to the convex set lecture. Yeah. Okay, so that's all I want to talk about in this lecture. Again, the most important part of this lecture is to understand the absolute value and understand why sometimes they can be reformulated as linear program. The fundamental reason is because of some convexity property. If you minimize a convex function, that is a convex problem, and since it is piecewise linear, you can use this trick to reformulate into linear program. And then the other way to think about it is that if you are minimizing z, then z will always take the tightest bound, right? But if you are maximizing, z will be unbounded, right? Okay, that's the main takeaway. And then in the next lecture, we will talk about some mathematical properties of linear programs to help you understand, why in a linear program there exists a vertex that is optimal.